In this video, I'm going to explain and show you the fundamental theorem of calculus. Now, the fundamental theorem of calculus says roughly that the following processes undo each other: finding slopes of tangent lines and finding areas of rectangle sums. The first process is called differentiation. And the second process is called integration. To say that the two undo each other means that if you start with a function, do one, then do the other process, you're going to get the function that you started with. So therefore, differentiation and integration are inverse processes. Now, there are actually two parts to the fundamental theorem of calculus, and we're going to take a look at the first part. So the first part requires that we use this integral of this form. G of x is equal to the integral from a to x of f of t dt. So notice that g depends only on x, and it appears as the upper limit in the integral. If x is a fixed number, then the integral will be a definite number. However, if we let x vary, the value of this integral also varies and defines a function x denoted by g of x. So let's take a look at an example. So here we have the graph of y equals f of t, and g of x is equal to the integral from 0 to x of f of t dt. And I want you to find the following values from g of 0 to g of 5. And then we're going to sketch a rough graph of this integral. So what we're going to do is take g of 0, which means that x here will be 0, and then we're going to plug in 0 into here. That means we're going to find the area from 0 to 0. So that means that this first value is going to be 0. G of 1 means we're going to find the area of f of t from 0 to 1. So that would be the graph from 0 up to 1 right here. So we're going to find the area of this triangle. So the area of this triangle is 2 times 1 and then divided by 2, which would give us an area of 1. Next, we're going to go from 0 to x value of 2. So we're going to go from 0, and now we're going to extend this area up to here. So we're adding 2 more squares, knowing that this first area was 1. We're going to add 2 more squares, so that gives us 3. Next, we're going to go to g of 3. So we're going to now go from 0 all the way to 3 in the integral. And finding this area, we're adding another 1 for that triangle. So now we have 4. All right, so g of 4, so we go from 0 to 4. We're now going to find the area underneath here. And actually, you know what? I'm going to make that area red to say that that is negative because it's below the x-axis. So my area that was 4, now I need to subtract 1. So that gives me 3. Okay, the last area is from g of 5, which is from 0 to 5. So we're going to go from 0 all the way to 5. So we have all of this green area, and we need to take away all of this red area. So we're taking away another 1 from what we had before, and our area was 3, so now it is going to be 2. So we're going to plot these values. So when x is 0, we get 0, 1 is 1, 2 is 3, and so on. Now, when we connect these points, they're not straight lines. So if we think about it, this is the graph of the slope, right? And what we're doing is, as we increase here, that means the slope is getting higher and higher. So we're increasing. So we start with a small slope, and then the slope gets steeper. It gets higher. So because remember that when we integrate, we're actually getting the graph of the original function. So when I graph this, the slope is small, and then it increases. So it's slow, and then it increases. And then from 1 to 2, it is a constant at 2. So I can draw this more of a straight line. And then from 2 to 3, notice the slope goes from a high value to a very small value. So it's steep, but then it gets more shallow. From an x value of 3 to 4, it's a small negative to a very large negative. So it's a small negative and then a large negative. And then from 4 to 5, it's a large negative and then back down to a smaller negative. So this whole side is a negative slope. So it's steeper and then it's less shallow. So it's steeper and then it becomes more shallow. So we have a graph that looks something like this. It's a little bit wiggly. Let me draw this a little bit better. So I'm going to erase some of these lines here. So it's a little bit clearer here. There we go. All right, now let's go on to the fundamental theorem, part 1. So it says in a direct way that integration and differentiation are opposites. So the fundamental theorem calculus part 1 says that if f is continuous on a to b on this closed interval, then the function g is defined by g of x equals the integral from a to x of f of t dt, where it is continuous on a to b and differentiable on the open interval a, b. And g prime of x is equal to f of x. So that means that if I take the derivative of g of x, then that means I have to take the derivative of the right side. So I'm going to actually end up with f of x. So this says that if you start with a function f of t, we're going to integrate it, then we're going to differentiate it back. You will get back what you started with, which is f of x. So you can also think of it as written as d dx, the integral of from a to x of f of t dt is equal to f of x. It seems quite simple, and it is. So in other words, the derivative of the antiderivative evaluated at the upper limit, in this case x, is the integrand evaluated at the upper limit. Let me show you a little demonstration. So let's take a look at the derivative of the integral of t plus 2 and show that it actually equals x plus 2. Now, you might think that the base or the lower limit matters, but actually it's irrelevant. So whether I integrate with 3 or 5, we're going to get the same value. So let's take a look. So I'm going to draw a graph of t plus 2. And we're going to start with integrating it from 3 to x. So 3 would be right here. And to x, we don't know where x ends, so we're just going to say that it's this whole area like this. So I'm going to color all of that in. So to find the area of what I've shaded in blue, we would say that it is the base. And let's say we don't know where this ends, so it's going to be a base of x minus 3. And then the height from here to here is going to be 3 plus 2, because that's what t plus 2 is. So it's going to be 3 plus 2. And remember, this would be an area of a trapezoid, so it's our height, kind of our base here. And then we have b1, and then we have this side here. So at x, we're going to say that it's going to be x plus 2. And then all of this is divided by 2 to get us the area of the trapezoid. So we're going to simplify. And this gives us x plus 7 inside these brackets, all divided by 2. So the area is x squared plus 4x minus 21, all divided by 2. All right, so that's what the area is. That will be just this integral part here. Now we're going to take the derivative of it. So dA dx states that this would be 2x plus 4 all over 2. And we simplify, and we get x plus 2. All right, so let's do the same thing with 5. So this time we're going to start at 5. We're going to find this area, again, also all the way up to x. So again, our base, or kind of our height, I guess, on this trapezoid would be x minus 5. And the height as first base would be 5 plus 2. And then the second base here would be x plus 2, all divided by 2. And we simplify. Inside the big brackets, we get x plus 9, all divided by 2. And we're going to multiply it out to make it easier. So x squared plus 4x minus 45, all divided by 2. So now again, we've taken the integral of this, except that instead of 3, we now have 5 on the bottom. And now I'm going to take the derivative, which is what it's telling me to do on the outside. So we get 2x plus 4, all divided by 2. And when I simplify, you will notice I also get x plus 2. All right, so to finish off, what this says is that the fundamental theorem of calculus part 1 states that all I need to do, if you compare, is take my x and plug it into the variable t, or whatever we call that variable. So in this first example, we're going to take x and we're going to plug it into t. So that means that g prime of x would equal 2x. And if we take the second one here, g prime of x would equal cos x. So like I said, it doesn't matter what the what the lower limit is. We just have to take the x and plug it into t.